All right, we're gonna get started here. As you've probably seen from this weekend's readings, we're gonna be looking at SQL today and relational databases kind of as a whole. Some of the things we're gonna be going over within relational databases is the idea of schema, what is that, indexes, data types, foreign keys, relationships. We're gonna briefly look at data normalization. Of course, we're going to talk about SQL and then tables and a couple SQL things like select and joins. Relational databases and SQL in general is a huge topic. We're going to try over this week to get comfortable using it, get comfortable making our own databases and schema and everything. But this is such a big topic that you could dive into, with even greater depth if it's something you're interested in. The science of databases is really big in terms of how do you optimize the database the best way? How do you make everything the fastest? So there's more and more you can go into, but we're going to kind of get the broad strokes today and get you guys up and running, storing data. So far, we've had some experience storing data in the past. We had, with TinyApp, we had just JavaScript objects that we were putting our stuff in, but this had a few drawbacks. Can anyone think of a couple drawbacks that our first TinyApp had in the way we were storing data? Yeah. You get lost in terms of like structure and things like that. It was Oh yeah, exactly. Yeah, because it was just stored in your program. Whenever you refresh the server, anything you had was gone. So that was a big one. That's the idea of data persistence. So there was no persistence when the app was restarted. Any new user data would just be removed. And the other thing that probably started to happen a bit was data could become disorganized. There was nothing like forcing you to do it in the correct format that you said. I know sometimes people, for example, with the user guys we had, you have an ID there. Maybe one time you store a user as ID or with the field ID, and then the next time you do underscore ID, you can just do that, and then down the line it causes problems in bringing it up. But then last week, we, with Tweeter, started to work with a real database. We used MongoDB. And this solved some of the problems that we had, specifically persistence. With MongoDB, we were able to create those tweets and then shut down our app, restart it, and we would still have any tweet that we made. So that was super good. With Mongo, the way we stored our data was similar to kind of those JavaScript objects, because that's with MongoDB, the idea is that you're storing like a JavaScript object directly in a database. And we stored them in collections. And each thing we stored, each user, for example, or I guess in this case, each tweet, was like a document. So Mongo has like a bunch of advantages. It's flexible. It allows us to store and retrieve data directly as JSON, which is something we're really familiar with using in JavaScript development. Ignore whatever this is. And we can have all the flexibility of our little JavaScript object that we had before. But it does also still have a few drawbacks or maybe a few compromises. Again, it's hard to search through sometimes. If we start getting those nested structure, we'll look at an example in a second, but that can be hard. It can also get disorganized. We still didn't have this thing where we decided on a very structured way of storing data, and it would only allow us to just store it in that way. With MongoDB, we could store it kind of any way that we wanted to. We could store it incorrectly or in different formats. So for example, if we have like our database here, say this is what our Mongo database looks like. We have one collection called books. And this is like all of our different documents inside here. We could have one book. It's got a name. It could have a author. And it could have a maybe like year. And maybe that's stored as like a number. And then within this books collection, we'd have like a bunch of books. So we'd have that one, another one, another one. Just get some quick books in here. I don't know when, 2012 or something. Anyone have a favorite book that someone wants that we should add? American Gods? Okay, that's good. Which one? Yeah, the director is like super killer too. This was Neil Gaiman, yeah. Hope that's how you spell it. So the first problem that maybe we could encounter is we have these 3 books, and then maybe we're inserting a new one. And in our code, we forget how we've stored it. So maybe we go date, and then we give it like a date object with like a different structure. So now that's the first problem that we would have encountered. There's nothing stopping us from storing it like this. And if we have code that's looking for specifically a year, and this one we have date, we're going to run into a little bit of trouble. The second problem that might come up is when we're storing data, data often has relationships with each other. So maybe we have another collection called users, and this is like a group of people. So our first user is a name. Maybe it's me. We could have a bunch of different key value properties, but maybe one of them is like favorite books. And then this is like an array of all the books I like. And I put in here like Dune, Name of the Wind, and then I put in like The Hobbit. So this is a nice relationship here. I have a list of all these books, and it's okay for the first 2 because these are referencing real books that exist in this book collection. But the third one, The Hobbit, doesn't exist in here. And what would be nice is if with my data relationships, if I have a list of favorite books, they should all be within this books collection. Because if I find a user and I'm searching through the books that they have under their favorites, I want to then maybe look up that book and get more information on it. But with MongoDB, there's nothing enforcing that our relationships are real, that everything listed in here exists within our books collection. Of course, if we were doing this, we would probably have these be referencing IDs, and all of our books have a unique ID. But even in that case, I could have an ID like it doesn't exist yet in my books collection. So there's nothing enforcing our relationships. There's nothing enforcing our structure. And then the last thing I mentioned, that it could be hard to search. If we start getting into this like nested format where maybe we had characters here, and then this is like an array of objects again. And then in here we had like name, I don't know, like some different characteristics about these characters. Now, if I want to search my whole database for a specific character, like I have all these lists of characters. Maybe I'm searching for like Duke Leto from Dune. I'm now going to have to first go into each book and then search the subarray of characters from that book, then go to the next book, search the subarray for that one, and it becomes hard to just do a quick search on a specific character or something, because I have to go first into books and then inside of each character's array within the book. Again, these are not like, it's not like you won't see MongoDB used professionally, because it is a very powerful database and it has a lot of advantages. But these, with any thing we choose in our stack, or any, say, database that we choose as a tool, there's pros and cons. And one of the cons for MongoDB is having how we enforce the structure, and how if we get really nested data, it can be hard to search. So with these two problems, one way that we can kind of solve them is with relational databases. So this is just a picture representation of how data is stored within a relational database. You have this column and rows layout within the whole thing called a table. So if we look at the top row here, we see the column names. So this is the data stored for the agent code, agent name, working area, commission, and phone number. And then within each column, we see the actual data for each of the entries. So entry 1, we have agent code 8007. The agent name is Ramasunder. The working area is Bangalore. Commission 15 cents. Phone number. And then for each next row is another record in the database. With this structure, these columns, so agent code, agent name, working area, has a specific constraint on what can be stored there. So agent name, this looks like a string. Within this database, any agent name I put should be a string. And relational databases will get mad at me and not allow me to insert, say, just like a number here. We'll explore more the constraints, but another thing, we don't get that like nested structure. So that might be a con of relational databases. Like I can't, within agent name, have like an object that has like more information broken down behind that. So that maybe restricts the level of flexibility I have in this database, but it helps in a lot of other ways that we'll see. So it's a database that stores information in tables, where each individual thing or entry in the database takes up a row, and each table can have relationships to other tables. They allow us to organize data in kind of pretty intuitive ways, at least when you start to see the patterns. So to start with, we're going to try and design some database structure of our own. So actually, before we even go into that, let's just do a brainstorm down here. Any topic or kind of field of interest that people have been getting into recently, something that we could explore with a database? What's something someone's been, like a new hobby or a new like thing someone's interested in? Yeah? JavaScript. Let's do something. Egypt? Like as a country? Okay. Egypt? Did I just spell Egypt wrong? Okay. Okay, so around Egypt, what are some like categories of things that we would be interested in? Pyramids? Or is there Y? No. Hieroglyphics. There you go. What's some other things? Mythology. Mythology. Okay, maybe a sub-topic under here is gods. What else? Let's get like one or two cities. Actually, that's probably good now. So we have pyramids, hieroglyphs, mythology, gods, cities. Okay, under pyramids, what's information that we would like to know about pyramids? Location, size, date, completion. Okay, what about hieroglyphs? Age, meaning, location, mythology. So just under mythology itself, you have stories. We could have like the time period or the dynasty. Yeah, same. Gods might be under it. Gods could have like name, description, superpower. Okay, nice. We got a little bit of a structure going. Okay, so we're going to build kind of a visual representation of the data that we just kind of laid out. So the first thing we had was pyramids. So we'll have a table that has pyramids, and then we want to store the location. And with location, or anything we store in a table with a relational database, we want to have a type. So what kind of information would we store in location? Like, what's the idea? Yeah, we could do a string maybe. Maybe we'll put it in brackets. And then we have the size. What would we do for size? Yeah, we could do like a number, integer, and then maybe we just know that it represents like meters or some form of measurement. And then we have a date, or we'll call it completed, and that would be like a date time. And for now, we'll leave that. But we can copy this, and we would have a second table. And this one we could do hieroglyphs. Whatever. And we also wanted a location, so we can leave that. We wanted a meaning, so that would also be a string, possibly. And then we also had a location. Oh, no. We also had an age. And that could still be a date. And then we would just have even more tables. This one being mythology. we had stories. Stories, which could be a string. We had time period, which could be, maybe we'll leave it a string for now because we said maybe time period or like the dynasty. Because it's harder to be specific. Like we can't give it a date object for like an Egyptian age. And then we also had gods, and that could be a string. Maybe we had God description, which could also be a string, and superpowers. Okay, the first thing we want to define is any relationships that our data might have with each other. So pyramids, hieroglyphs, mythology. Oh, cities. Cities would actually be a really good one. We'll quickly do cities. Cities. We'll just leave that similar stuff in for now. So we have these 4 tables, but each of these tables could have relationships with the other table. So a city could have pyramids in it. It could have mythology associated with it. So we can make a relationship between one to the other. Let's give ourselves a little more space. So firstly, those 2 relationships I said could be a thing. Cities could have pyramids. They could also have maybe mythology associated with it. What are some other relationships that we could have with this data set right now? Yeah, we could have hieroglyphs in pyramids. So a pyramid could have hieroglyphs. There could be a hieroglyph for a city. Hieroglyphs could be about specific mythology. So we start getting a lot of relationships. Our data is like pretty interrelated in this part. The second thing with relationships, we have to think about how the relationship looks. So what I mean by that is one city could have exclusively one pyramid with it, maybe. That sounds about right for a city and a pyramid. A pyramid can't exist in 2 cities, for example, because it's in a single location. So for every pyramid, it'll have at most 1 city. But a city could have multiple pyramids. So in this case, we have a one-to-many relationship. One city could have many pyramids. So maybe we can do that with just a little, we'll add an extra set of arrows on this side. So there's one city, it could have many pyramids. There's also, like, we can look at the other ones. So a city has mythology associated with it. Maybe in this case, we say that we're going to define mythology kind of broadly so that a city can only have one mythology and a mythology can only be associated with one city. That's probably not realistic to how the actual history of mythology works, but then we would have a one-to-one relationship. Each mythology can only have one city. Each city can only have one mythology, maybe. But with a city and hieroglyphs, or maybe we'll do a pyramid and hieroglyphs, one pyramid probably has many hieroglyphs within it. So we would have a one-to-many relationship again. And then the same with like maybe a city to this guy. So within relational databases, the way we make these relationships is with foreign keys. But first, to even have a foreign key, each table that we have has to have a unique identifier associated with it, so an ID. So our city would have an ID. Actually, all of our tables would have an ID, which is just a unique identifier. In most cases, can be done with like a number. So our hieroglyphs would have an ID, and then our mythology would have an ID. And then for these relationships, if a city has multiple pyramids, we can have another entry in our table that has a reference to the relationship's ID. So we could say a city has a pyramid ID. So then when we look at the city information, we can see which pyramid is associated with it. Or like a city could have a specific mythology. So let's do the mythology first. Come on. I'm just going to move these down a little bit. So the easy example is to go mythology ID. So then with a one-to-one relationship, it's pretty simple. Every city, I just have to look up the mythology ID, and then I can look through the mythology table to find the specific mythology that is associated with that city. So one-to-one, you just pick one of the tables to have a reference to the other. I could also, within here, have a reference to city ID, but that would kind of be redundant in the sense that I can already look up, I already have defined this relationship with an ID on this side, so I don't need to put another thing here, because just with this ID, I can know that they're related. I don't need to also have this one be back related to it. So one-to-one, you just pick one of the tables, and you can put a foreign key, which is in a reference to the other table by the other table's ID. When we have cities to pyramids, this is a little different. So maybe if I just, OK, let's decide I'm going to add another thing here, and I'll do similar to what I just did. I'll say pyramid underscore ID. So now a city that has a pyramid, I just look up the ID here, and I can find the pyramid in the other table. But in this case, we said the city had a one-to-many relationship for pyramids. So pyramid ID is a reference to a single pyramid. If I wanted to store many pyramids to a city, and I have a pyramid ID here, well, I kind of run into a problem. Because if my pyramid ID is 3, and I have pyramid 3 associated with the city, and then I want to add pyramid 4 associated with the city, do I just delete 3 and add 4? Now I don't have a reference to the first pyramid. Or maybe we can think, well, in MongoDB, we could store arrays. So maybe I'll go 3, 4, and now I have this array of references to another table. But within relational databases, you can't store arrays or objects or things. It has to be simple data types. So that's another thing that we can't do. Well, then maybe we're going to say, we'll just keep adding pyramid ID 2. And now we have, like, we can store the second pyramid in here. But then we're just going to have to be, having more and more columns in our table to store all of the different pyramid IDs. Instead, the better choice is to say, while a city can have many pyramids, each pyramid can only have one city. So if I decide to store the foreign key on the pyramid side, where I go city underscore ID, then I'm kind of fine. Because each pyramid, this pyramid is associated with city 1, can have one city. And then if another pyramid also has city 1, that's fine. And I have, each city can have, this pyramid could have, this is going to get, can have another pyramid over here with, I could put city ID 1. So we have a one-to-many relationship. So the rule is, when we're doing relations within a relational database, the foreign key, so this city underscore ID, if it's a one-to-many relationship, the key goes on the many side. So we have one city to many pyramids. The key goes on the many side, the many being the pyramids. So any questions about that relationship, one to many? The next thing that can happen, so we have one-to-one, which was kind of simple. We have one-to-many, which was still fairly simple, but you have to remember the foreign key goes on the many side. But there's a third type of relationship that we're going to run into some more problems, and that's a many-to-many relationship. So if instead of having the kind of naive assumption that each city could only have one mythology and each mythology can only belong to one city, what if we say that each city can have multiple mythologies to it, and each mythology can belong to multiple cities, which is probably more close to the truth. One city, they're maybe sharing different mythologies, and a mythology can span over different time zones, so it could span over multiple cities. So what we would probably have here is like many cities can have many mythologies, and vice versa. So the same way we ran into the problem where, well, if we put the foreign key here, if we put the foreign key here, well, we have to keep track of many mythologies. So we couldn't store like a single mythology ID. We would have to store an array of mythology IDs. So then we say, okay, well, if we can't do it there, let's do it in the mythology side of things. Well, here too, we would have to store many. I'm not sure why that's. We'd have to store many like mythology IDs. So we're kind of stuck on either side. When we have this many-to-many relationship, I can't store many mythology IDs on the city side, and I also can't store many, I guess this would not be many city IDs on the mythology side. So given the restraints that we've said, that a table can't store arrays, there's kind of no way I can do this with just two tables. So the solution when we have a many-to-many relationship is to create another table. And this table's specific purpose is to join cities to mythology. So we call it city underscore. And there's a specific name for this type of table. It's called a join table. So when we have a join table, we don't have to really, its main purpose isn't to store data, but just to describe a relationship. So we don't need to have data within it. But we would have two foreign keys. So we would have, it has a mythology ID already, and then we would have a city ID. Okay. So with this join table, we can, so we want to do many-to-many. And instead, we can do that in two steps. We can say each city can have many relationships with mythology, and each mythology can have many relationships with a city. So in doing so, we say each city has many joins with mythology, and each mythology has many joins with this city with this city mythology join table. So we get by having to store multiple foreign keys in any location, because there can be many city mythologies, each with a reference to a single city and each with a reference to a single mythology. So what we have going here, let's look up some. So we have, probably a couple different cities. And then on the other side, we would have, I'll just do something like this, the mythology associated with that city. And we said there can be, each city can have, multiple mythologies. But each mythology can also be associated with more than one city. So this is the relationship that we're having right now. And our problem with our naive single table, one table for cities, one table for mythology, is that here we see there's multiple arrows leaving the city. So we can't store the foreign key there. But also with some of our mythologies, we see that there's multiple arrows leaving the mythology itself. So when we have multiple arrows out and multiple arrows in, or multiple arrows out on either side, that's the problem that we have. Instead, if we define something intermediary, so we have this, for some reason, intermediary cube, and we say anytime we'll get rid of, so we have this guy wants to be with this one and this one. So, and then this city wants to be with that mythology. It also wants to be with, we're going to space this out a little more. So we have one. So we have 5 relationships that are defined. So now we'll go, well, this city is related to this cube, and this mythology is related to that one. The next one we wanted to was here to here. So similarly, we go related to the join table, and the mythology is related to that join table. And then we'll do a similar thing down there. And then for our second city, we can be related to the same set of mythologies if we want. So this one and this one. And now if we look at our pattern, none of our entities, whether a city, mythology, or these join tables, has more than one arrow entering or, well, no, wait, sorry, that's not true. So all of our join tables have no more than one arrow entering or leaving it. So one arrow coming in, one arrow coming in, one arrow coming in, one arrow coming in. There's 2 arrows, but they're of different types. So this is a city arrow coming in, and this is a mythology arrow coming in. Meaning we can store it in the table with just a single city ID and a single mythology ID. Same with any of these cubes right now. And then with our city, where we have 3 arrows leaving, we don't need to store any information about where they're going because it's already stored in the join table that it's accessing. So same with the stars. So that is our way to kind of get over many to many. You have to define an additional table in the relational database. But with our one-to-one relationship that we had earlier, we're fine. And with our one-to-many relationship that we had, you're also fine. The case with the one-to-many, the foreign key goes on the many side. All right. So in our example there, we saw a few things. The schema of a database is a skeletal structure representing how data is stored. It specifies the constraints on the data. So here, our text for a city, like the location, and we said it can be a string. Its size is an integer. Its completed field is a date. Then it has an ID and a mythology ID, which are both of types ID. That's our schema, essentially, for our city table. We also had indexes. Each of our things had an ID, which is its index. An index is just being a unique identifier. So we can identify a city, even if two cities had the same name. There's a Vancouver and Washington. We're in a Vancouver here. They would be unique by their ID. IDs are used to build relationships between each table, but they also help improve the speed of data fetches. So behind the scenes, when we're doing a search for a specific city, an index makes that faster. And then part of our schema is that we had data types. So defining our columns for the tables, you need to specify what data can be stored by the relational database. You have varchar. Within our relational databases, your data types get broken down into more distinct types. So we don't just have a generic string. We have varchar and we have text. Varchar being a string where we specify a specific size. So we could say varchar for Twitter, what 140 characters was it? You could do varchar 140. So specifically, we're going to use 140 characters at most in whatever we store here. Text is a longer form. Text, I don't know the limit on it, but that's like if we had a description field, we might use text because it can just store a lot of information there. We have Boolean, we have date that we've seen in JavaScript. The primary key or our index uses a type like serial. And then you can also specify additional constraints when you're declaring your schema. So serial being the type, serial is just a number that is unique. So if our D is serial, we insert one thing, it'll be 1. The second thing might be 2. The third thing might be 3. At no point later on when we're inserting something can we insert something with the number 3 again. It's a unique number. And then primary just means that that's going to be our index, or primary key, sorry. And then the last thing, we can also say, for specific data in our table, we don't want it to be empty ever. We don't want you to be able to insert maybe a city with no location. If you're going to try to do that, we'll give you an error. So we can add not null on the end of our schema when we're specifying the column. With integer, you have also like some options the same way you did with string. If you're getting deep into the negatives, you can use, or if you're using a smaller number, you can use small int with negatives. If you want to do an integer, that gives you a wider range of numbers. And then big int is if you're going really big with your numbers to numbers that like you wouldn't even be able to like think of. And then serial, that's the thing. It auto increments from 1 upwards, only positive. There's a brief thing here that talks about when you have foreign keys. So when we have mythology ID, or let's do a simpler one, when we have a city ID referencing a city from our pyramids, a pyramid always is going to have a city that it's in. So you can add this thing where you tell it that this city ID references a city. So we would say explicitly, this isn't just a random ID, it's the one that's referencing a city. And then we can also add an additional piece of information on delete cascade. And we're going to look more in detail at this, I think, in the breakout. But just briefly, we can think of a case here maybe where a city has a lot of pyramids. and then maybe for some reason in our data, we're removing that city from our data. We say, like, we don't want to like track Cairo anymore. Let's delete that city. Because a city has pyramids, something that makes sense with that relationship is if we're going to delete that city, then we should also delete all of the pyramids associated with it. If we have a bunch of pyramids for a city that we're not even caring about, it kind of is like unnecessary data. So if we specify on delete cascade, we're saying that when you delete, if this pyramid references a city, if that city is deleted, also delete the pyramid. That's all that this on delete cascade is saying. So the point is, when we're defining the schema for our databases, we have a lot of different options in how we're constraining what gets stored. Constraining being our pyramid can only store a location with a string, and we don't want that location to be empty, maybe. For the structure of our relational databases, we want to use snake case for our table and column names. So I think I tried to do that for the most part here. Time period wasn't, but like super underscore powers, God underscore description. Oh, actually, one thing that we should have done here that would illustrate something nice. So within our mythology, we have like this information on gods, or I guess it would probably be a single god, and then the god's description and the superpower. What happens then if we have multiple mythologies with referencing the same god? Like this mythology has what's a Egyptian god? Set. And this mythology also references that same one. And then down the line, we change the description of that god to be more descriptive. I'm going to then have to edit the description in this entity. And then I'm going to have to find the other mythology that has reference to that god, and I'm going to have to edit here. The better solution would be to have a new table. Called gods that has all that information separate. And then we exclude it from mythology. We just create another relationship. So now instead of including all that really long information that could be repeated within multiple mythology tables, we exclude it once in another table, and we just have like a new reference to it. We'll look at that a bit more in a second. But yeah, so naming convention, we want to use snake case. We want to pluralize the table's names. So this is called cities. This is called pyramids instead of city or pyramid. And then our column names are singular. So location, not locations. Stories was that we would be storing multiple stories there. So this would probably be another case where we might want to make another table just for stories. But the table name will be plural, and our column stuff is singular. We saw this, like foreign key is a field or collection of fields. This join table had more than one field. It had a city ID and a mythology ID that references the primary key of another table. The table containing the foreign key is called the child table, and the table containing the candidate key is called the referenced or parent table. Candidate key just being the one that's being referenced. So our city has many pyramids. The city is the parent table. The pyramids is the child table. Foreign keys can't be null. So like we said earlier, if we're deleting a city, we don't have a city to reference. That's something that we can't do. I can't have a city ID that references no city, because when we're building a relationship, the idea is every child should always have a parent. So every pyramid should always have a city in this example. we saw these three relationships. We saw the one-to-one, the many-to-one, and the many-to-many. The many-to-one, we always have to put the foreign key on the many side. And then in the special case where we have many-to-many, we're going to need to make a new table called the join table that helps us join many-to-many. Lastly, an ERD is just what we made here. It's a diagram representing the schema of the database and illustrating the relationships with like usually some form of arrows between each of your tables. If you have a one-to-one relationship, it's usually just a straight arrow. If we have a one-to-many, it's this, they call this like a crow's foot arrow. So the arrow branches on the many side. And then the other thing we could do for like inferred relationships or like, so cities is related to mythologies through this join table. So we could just create like a, this is the worst tool, this one. It should be like a dotted line. So there's not an exact reference from cities to mythology, but they are related through this other table. So you could put like a dotted line to indicate that relationship. Database normalization, we started to see that with this mythology thing that I just said. We had all this gods data within mythology, and that data could be repeated. If we have multiple mythology entries in the table with the same god, that's like repeated data. We have, we'll look at an example actually, it'll be better. But it's the idea of reducing duplicate data. So here in this example, we have a table that stores albums and the artist's name that like who produced the album. So we have all of these albums here with each limited album that they created. But the problem here is we can have duplicate data. If any artist has multiple albums that they've created, their name will be repeated twice on this right-hand side. So Snoop Dogg, we have like his 2 albums that we've included here. So his name is included twice on this right-hand side. We have duplicate data in our artist name column. All of the rows for the same artist will be duplicate. So this is an example of a denormalized database. If we just have a mythology with all the god information in here, it's denormalized. To normalize the database, the usual step is to create a new table. So to normalize this guy, we're going to split our albums table into a table for albums and a table for artists. Again, like if Snoop Dogg here, like he decides to change his name back to Snoop Lion, we have to go into row 4 and edit his name to Snoop Lion, and then we have to go again into row 7 and edit his name to Snoop Lion, and then so on and so on for all of his albums, changing and updating his name. That means like we have to do, like he's got a lot of albums, like 12 updates or something, instead of maybe just 1. We have 12 repeated instances of his name in this table. And if we forget one, then we start to have like data inconsistencies. If he's Snoop Dogg here, and we forgot to, or we edited this one up to Snoop Lion, now we have like inconsistencies within our table. Instead, if we split it into an albums table and an artist table, then we only have 1 row for Snoop Dogg, which is referenced twice in the albums table for his albums. Now, if we ever want to change or update an artist's name because they're changing their name, we have a single source to change it. I only have to edit this 1 row, and all of these albums will be updated as to their artist name. The other benefit is just in how much data I'm storing in the database itself. This is just taking up the very limited space of 1 row with like however many characters that is. Whereas before, if our database gets really big and those artists start releasing like, in a weird world, hundreds of albums, it's just taking up so much more space to store their name 100 times versus 1 time. So this idea of like breaking a table down, usually into smaller tables, because you have repeat data, that's database normalization. Database normalization can get more complicated than this kind of like simple breakdown. But in general, like if you keep a good plan of data at the start, you can keep it this simple. The problem with database normalization is if you jump into building a database, creating a lot of complex tables, and then after the fact trying to bring it down to something simpler, that's when it can get more complex. Here we show that each album belongs to an artist. The details of the artist are stored separately. When we need to gather this information together, we're going to have to do a query to first ask, what is the artist ID for this album, one, and then we'll have to do a query to check, oh, in the artist table, one is Kanye West. If we need to change the name, like this is, again, one of the main benefits, we only have to change the one field in the artist table. We're going to take a break for like 10 minutes and come back at 10:10. If you think of any questions during the break, or save them, and we'll come back and try and answer anything that comes up right when we get back into it. Okay, let's get back into it. So we've been looking at examples and kind of design. The design that we made was a relational database. But with actually programming and our applications, we need a specific relational database itself. So you have relational database management systems. They're the actual implementation of relational databases that allow you to create databases, manage them, do searches with them. Some examples are like MySQL, Oracle, Postgres. There's like many relational databases out there. For our purposes, we're going to be using Postgres, both kind of this week a bit and in future weeks. That's the relational database management system that you'll be focusing on. But throughout all of these, they're very similar. One of the ways they're similar, they all use SQL. Well, like pretty much all of them use SQL. There's like one or two like weird ones that don't. But SQL is structured query language. So it's a language that allows us to look for, query, and insert data into an SQL database. Like I said, pretty much all relational databases are going to be using SQL. But SQL is not like other programming languages. So we've been using JavaScript a lot. We're comfortable with that. It's not a comprehensive thing like JavaScript. So don't get too worried about learning it. SQL is specifically for data. Like you can't write full programs in it. You can't do like logical stuff. You're just using it to like insert stuff into the database, update stuff from the database, and mostly to search for stuff in the database. When we're using Postgres, we have this nice command line tool, PSQL, where we can interact with our Postgres databases through SQL commands. If I go to my terminal here, and I do PSQL, I'm now like logged in as Travis. I'll get this a bit bigger. And I can, look at my databases and tables and stuff like that. If I go \L, I can see the, different databases I have here and the different owners and information on it. And then if I go \DT, depending on which database I'm currently in, I would see the relations for that one. If we want to create a table with databases, we know what our schema looks like maybe already from our entity relationship diagram, and we can use this information to create a table within a database. So maybe with ours, we would go create a database, and we could call it Egypt. I hit enter. It says create database. So now if I go to \L, I can see that Egypt is here. I can then do \C and specify that I want to connect to the Egypt database. And now, once I'm in that database, I can create a table inside there. So I can go create table. What was our first one? Maybe we'll go cities. And the one thing that's going to get in, well, it's helpful, but it's initially going to be kind of annoying within, if you're using the SQL stuff in the command line. The line doesn't get executed until you put a semicolon in. So if I hit enter here, it just continues my command. So this is nice in that I don't have to do everything in one line. But you'll do simple searches and forget to do the semicolon, hit enter, and nothing will happen. It's because you forgot the semicolon. So we want to create a table cities. We want to have an ID. We make it serial, primary, it's the primary key, and it's not null. We also want a location, and we said that would be a string, so in our case we could do varchar, and maybe a city's no more than 150 characters. And then we can do completed, which is a date. What were our date options? We had date, timestamp. So date is if we just want a day, month, year. Timestamp is if we want down to the actual second and having the actual time. For this one, maybe we'll just do date. And then we had a foreign key reference to city mythology. This should be city mythology. We'll leave that for now because we're not going to put that table in for this example. So if I hit enter now, of course I'm going to get a syntax error. Let's see. Completed. Sorry? Comma after the date. Oh, it's probably that. So we go up. Get rid of that. Yeah, there we go. So it said table, create table. So now if I go /dt, I can see that I have one table called Egypt. Schema has name, type, or no, let's, this is the relations. So it doesn't have any relationships. But if I do, we'll see in a sec how to query stuff, but let's just go select all from cities. We can see it has 3 columns: ID, location, and completed. There's no data in there because, of course, we haven't added anything. But that's how we will create a table. And then if you want to insert something into your database, you have a similar command. You can go insert into, you specify the table name, and you specify the columns which you're adding data to. So in this case, we're adding ID and name into the artist table, and then you give it some values. So 1 and the name. Another example of that same structure. There's another type of syntax if you need to insert multiple records at the same time. We don't want to be repetitive and say insert into artist ID name 1 name, insert into artist ID name 2 name 2. So you can do it with insert into tracks, again the same thing, and then values, and you just give it a list of values that you want to be inserting into your data. So maybe we want to insert a city into our database. We can do it in the command line with PSQL, but as you saw, if I have a syntax error or something, it can get kind of hard to go back and edit this string here. I have to tab through my commands. It's also hard to see if I missed a certain comma. So the alternative that we'll be doing is we can open up a file, and we can do any SQL commands in this file, and then we can run this file from the command line and get it to execute. So if we wanted to do an insert maybe into our, we'll go insert into cities, and then we had values. Our city had a location. We had a location and completed, comma, completed. In any case where you have a ID and it's of type serial, you don't need to be explicit in what the ID is. Because the ID needs to be unique and it's incrementing, you just let Postgres or you let the database handle that itself. So if I leave that blank, Postgres is going to insert its own unique ID in there and it'll handle it myself. In fact, if I want to specify explicitly an ID for this thing, I can run into trouble. So the key is to leave it out, and you just specify the stuff that's, you know, kind of we know that is specific to our information. So insert into cities, values, this, and then we wanted to go we want to insert those things, and then we want to give it the values. Here is where we specify whatever we want to do. So we could go, is that how you spell Cairo? And then we would have to give it a date, but I don't have a date right now, so I'm just going to give it, I don't know if that's going to get mad at us, but we'll see if that works. And then in our command line, I can go /I, and I can give it queries.sql to run that thing. No such file in directory. Let's see where we are. Actually, there we go. So I'll reconnect, and then I will reconnect to the Egypt database, and then we'll run /I, the file that is in this directory, and it's called queries.sql. Cairo does not exist. Oh, the other thing that we're going to need to be careful with is what type of quotations that we're using. So when we use double quotes, SQL is thinking that we're referring to a table name. Single quotes is for data. Again, I'm not sure if we can force this date type, but we'll see. Out of range. So if it's out of range, maybe we just make it smaller. Okay, maybe for now, we'll just leave the date out just to see something inserted. We didn't say that date was not null, so because we didn't create that constraint, we can add a city without a date. So we have 1, 0, 1, that this 0 means whether it's fair. Like the first number is if there was an error. The second number is like whether it was successful, I believe. So 0, 1 means no errors, and it was successful. Now if we go select all from cities, we can see that I have one row with the location Cairo. We didn't get to put the date in, but that's okay. And then, yeah, this is the alternative syntax if you want to just like insert a bunch at once. You already saw me use select just a second ago. The select syntax for SQL is likely to cause the most confusion. There are 6 different clauses that you can use to query for data. So you have select, from, where, group by, having, and order by. Select, that says which columns that you want to have returned. In the example I just did, star means everything, but I could go select location from cities. And in the data that I get returned, I'm just getting the location column. So select, you can specify which columns you'd like returned. From, that's which table you're selecting. Provide one or more tables from where you want data from. So in this query, I'm getting it from cities. I'm specifying that I'm just getting data from a specific table called cities. Where, this is any filters that we're going to get from our search. This is kind of what makes searching useful. Only select records that match the condition. So I could do select all from cities where the date is greater than a certain time. We have group by, having. These two have to do with aggregates. Aggregates being if we have a big list of stuff that we returned, we can count the total number of rows. We're going to look at these in a bit more detail later. But for now, we're just going to focus on select from, where, and order by. Order by just being we can order the results that come back. It doesn't affect what's returned to us. It just affects how they're ordered. So for the remaining examples, we're going to be looking at a kind of like a music relational database. So to do that, first we are going to create the database music. Okay, so we're going to drop the database music. I don't know what's in there. So that's gone. And then we'll create it again. And then we'll connect into that database. And I pre-made kind of a setup SQL file. So if we look at this file, it's long. It creates each table and then inserts a bunch of data into it. So here we see we're creating a table artists. It's got a primary key and it's got a name with varchar 50. An album table, same. It's got a primary key. Each album has a title, a year, and an artist ID, which is a foreign key that references the artist table. Tracks has a ID, title, a number. So is it track 1, 2, 3 from that album? And then it has an album ID, which is a foreign key that references the album. So our tracks reference albums, our albums reference artists. We have that relationship set up. And each of these, so we have a one-to-many relationship for each of these. There's one artist can have many albums, one album can have many tracks. And then there's these last two tags and artist tags. So this is where we have a many-to-many relationship. Tags are like the genres. So tags, we have hip hop, rap, electronic, rock. And then artist tags is the join table. It joins a tag to an artist because one artist can have many tags. You can be an intergenre artist, and each tag can have many artists. There can be more than one, hip hop artist. Each artist can be maybe hip hop and rap. So that's why we have the many-to-many. And then down here, I just have a bunch of, so, we're inserting an artist, and then their album, and then a list of their tracks. So if I run /i setup.sql, I hit enter, we get this big string of inserts. The other thing you see at the top here, I have drop table. This, all I'm saying is if this data is already in there, remove it and I want it to be re-entered. This lets me kind of have a fresh start anytime I run this setup. So these notices are just saying that we just created this database from nothing. So there's no artist tags. I can't delete it. There's no tracks. None of these tables exist. We can't delete them. So then we're creating the tables and inserting all this information. Okay. So back to the queries that we actually want to be running. So if I want to get the name and ID of all artists, I can go select name, ID from artists. Semicolon, I hit enter. I see my return right here in the console. We have these 6 artists that are in our database. If I want to see Daft Punk's albums, well, I'm going to select all from its albums. So I want to get albums. But then I need the where clause. So where, and what do I want to specify in this where clause so that I'm only getting Daft Punk albums? Any ideas? Yeah, so I can go where artist underscore ID, and then I can, it's just a clause that's testing if it's true or false. And because I already did this select up here, I know that Daft Punk has an artist ID of 5, so I can go where artist ID equals 5, semicolon, and I hit enter. And now I'm only getting the albums where the artist ID was 5. So I can see that he had, you know, these 4 albums, at least in this small music database. Next, if I want to see all the songs of the album Discovery, well, Discovery is one of Daft Punk's albums. So the songs, again, I could go select all if I want to from tracks where, and again, we're going to do something similar to what we just did here. We said where artist ID is 5 because the albums has a relationship to artists and our tracks have a relationship to albums. So we can go where album ID equals, and then we're going to look down here because this is the album ID. It's 5 as well. So we'll go 5, hit enter, and now we're just getting the tracks where our album ID is 5. Whereas if I go just get all from tracks, I'm going to get way more stuff. So this is all the tracks as opposed to just these 14 ones. What are some other things we can do? So yeah, here, in both these cases, we need to know what foreign key we want to reference. So that's something to think about. If I don't have this previous knowledge of what the artist ID is or this previous knowledge of what the album ID is, it's kind of hard to do this query. If I want the name and year each album was released ordered by the year, so we're going to go select. If I just want the name and year, I can specify name, year from, we're talking about the album table, and then was name and year, each album was released ordered by year. So I want all of them. I don't need a where clause because I want everything turned back. So I can do order by, and then I can say year. Album, oh, yeah. So we need the plural. Name does not exist. Oh yeah, because our albums, they don't have a name, they have a title, I believe. So there we go. We get all of the albums in the album table, and we see that their year is going from 1997 up to 2017. If we wanted to maybe go descending, we can say order by year descending, something like that. Yeah, there we go. So now it's the reverse. So order by, useful in ordering the data in the order that they come back. We could also do order by name, and it'll do it. Oh yeah, because name doesn't exist. We could do order by title, and we'll get like A through T. So yeah, we did order by year, and then you can specify additionally. We saw if you want it descending. The default is ascending. We can switch it to descending. I want to see how many tracks there are. So this is where we're getting into aggregate functions. That's something that we talked about before. We saw up here. Group by and having have to do with aggregate functions. So if I want to see how many tracks there are, what I can do, I want to select, let's check out our schema. So tracks have a title. So maybe I'll do, this is an aggregate function. So I say count, and I say title. Select from tracks. Is that what you said? Is how many tracks? How many tracks are? So we from tracks, and if I hit enter, I get just one row or one column returned with one row called 140. So the aggregate function count takes all of the stuff that was returned and squishes it down into like one. It counts the number of titles that were returned. So 140 tracks in the thing. If I wanted to be a little more clear, you can select things. So similar, you could do it with the same way we were doing select before. You can do it with aggregate functions, and you can rename what the return data column will be called. So I can go select count as track count. This doesn't return. This doesn't return what is like the data that's returned. It just changes how it's labeled. So we counted all of the tracks, and we returned it to the table track count. Count is checking how many rows exist in that column. So it kind of doesn't matter which column we specify in this case. If I go count ID, we hit enter, we get the same result. It's not counting, like the ID has numbers in it. It's not like tallying all the numbers in it. It's just counting the number of things that exist in that column. If I want to do an actual like tally, I can go sum. And if we sum up our IDs, we get a much bigger number. This number is probably useless because it's our primary key, our incrementing number 1, 2, 3. It doesn't actually represent any data, but maybe we had in our cities table here, maybe we had an extra property called like population, and we wanted to see the total number or the total population across all of our cities. We could do select sum of population, and that might give us some useful information back. If I want to see how many tracks there are for a specific artist, we're going to do something very similar. So I can select ID as artist 1 tracks from tracks, and then I can say where artist underscore ID equals 1. Column artist ID. Sorry? Yeah. So here we want to see how many tracks there are specific artists. That is hard because the artists are kind of 2 relations away. So our tracks are related to an album, and our albums are related to an artist. So we can see how many tracks there are for a specific album, but to get how many tracks there are related to a specific artist now becomes hard. using the type of queries that we have so far, there's actually no way that we can solve this. Because if we do, OK, let's find the albums associated with an artist. Well, I guess there is one way we could do it. We could have like a multiple where statement. So we could go, what are the albums associated with artists? OK, artist 1 has album 5, 6, and 7. And then here, I can go where album ID equals where album ID equals 5, or album ID equals 6, or album ID equals 7. But that's starting to get like not very clean, not very fast. But if I just want to see the tracks from a certain album, I can do that, and I see whatever album with the album ID 5, it has 14 tracks. But this like double relationship away is hard with our current level of queries. This is like a similar problem. If I want the first tracks on all albums released by Kanye West, so tracks being stored here, and the artist information being stored here, I'm going to find all the tracks whose number is 1. Currently, that's just with our simple from and where clauses. I can't think of an easy way to do that. So we would have to say, OK, again, let's find all the albums who have the artist ID of 1, which is maybe Kanye West, and then let's search all of the tracks where the number is 1 and the album ID equals one of those ones we found before. So we're getting to this like multi-step kind of like problem. But luckily, SQL is pretty powerful, and there's a way that we can fix this. And that's with joins. So joins is a way of, well, joining two sets of data, two tables together, so we can do a single search on it. There are many different types of joins. These circles are representing the data in 2 different tables. So a left join is where we take all of the data from the left table and we join it with the table on the right, but we keep only the data that exists in the left table. So if there's a match in the right table that doesn't exist, we don't return that. Full outer join returns all of the data matched together from both left and right. These last 2 we won't think about. Inner join returns only when there's a direct match. So it returns only the overlap between the 2 tables. And right join is just the opposite of the left join. You can specify these different joins with some different levels of syntax. The default is inner join. So if you just say join, it's an inner join. Left join, also called left outer join. Right join, also called right outer join. And the outer join, also called full outer join. So when you're performing a join, you define the type of join and also the 2 tables involved and what you're joining on. So this on condition is what we're joining on. If we have an artist table and an albums table, the thing that makes sense to join those 2 on is the foreign key. We're joining these 2 tables where the album's artist ID equals the artist's ID. So then we get one combined table that has all of the relative data from both tables mixed together correctly. So let's look at that quickly, actually. Select all from artists, join albums on artists. Nope. Score ID equals ID. Before I enter this, does anyone see any problems that might occur with this? But I've said that there's it has reference to both the albums table and the artist table. So it will know that album ID comes from albums. But the problem is with ID. Both album table and artist table has an ID. So when I say equals to ID, I'm kind of ambiguous as to what I'm referring to. So if I hit enter, well, it's also saying album ID does not exist. Albums. Oh, it's a. Oh, yeah. Because what am I joining? Artists on albums. Yeah, that's a big jump. We can't do that. So, oh, no, we can't. Artists on albums, and then the albums has an artist ID. OK, let's fix this. OK, so now this won't be a problem. Error. Column references ID is ambiguous because both artists and artist ID both have IDs. So whenever we're doing joins, we have to be explicit in how we're naming things. So we can do select, if we're selecting the ID from artists, we can do ID as artist. Just do art ID, and we'll also do name as artist name. So now if we hit enter, column ID is ambiguous. So we're still not specific enough for it. So what we can do is we can target it specifically by specifying the table and then the property that we're accessing from that table. So even though we're renaming ID as a separate thing, it still wants us to be explicit here. So we can go artist.id. And if we hit enter, what do we get? Missing from clause, entry for table. From artists. I think we're just like doing something else silly. So select those guys from artists, join albums on. Okay, let's try one more time. Yeah, so we'll, I don't think it's the rename, but we'll get rid of that. From artists, join albums on. See, this is where we should start using the separate file to do our queries because it gets really hard to error check and correct stuff right in the command line. So this is from album. Missing from clause for table. Okay, yeah, let's move over to our queries thing. So we can see it a bit clearer. So we have select artist ID, artist name as artist name. We're also getting the album title as album title from artists, and then we're interjoining albums on artist ID equals the foreign key referenced here. So we'll save that, and we'll go /i queries.sql. What? Missing from clause entry for table artist. The S. Artists. It should be, oh, here we're going. We need S's for all of these things. Artists, no, we don't. Oh, here. That's probably what was doing it. Missing from clause entry for table artist. Well, normally, so when we're selecting a specific property, we're selecting it from a single artist, so we do not plural. And then when we're selecting the table, we want to do plural. So what's the specific error? We're saying missing from clause entry for table artists. We give all of these, I don't think that's, oh, my bad. So now we see the join results. So we have artist name and we have album title, which are from separate tables. Artist name, that's in the artist table. Album title, that's from the album table. So with the join, we're able to get both information back together in a nice set of things. But this was an inner join. So the data here is only data where we had a clear match on ID and artist underscore ID. For example, if there's an artist that doesn't have an album, with an inner join, they're not going to show up here. So if we come back and like the example here is if we have this up and coming artist, actually we'll do both in the same line. Nizi Boskarizi, and we're not going to specify his ID. And we first insert him into the table. So we'll comment this out for now. So we run that query. Duplicate key violates constant. So this is earlier when I said if you explicitly tell it an ID, it messes with Postgres's internal ID clock. If you look at our setup, when we're inserting artists, we're giving it an ID. So to Postgres, it thinks that it's on the first thing that it's inserted, because if the only ID that it's been in charge of incrementing has been this one that we just tried, but we already force made one with an ID of 1, so it's giving us an error. That's why you don't want to specify ID when you're inserting stuff. But now, because we've done it that way, we're going to have to. And so we'll also have to give it a really big number, because we don't want to reference an artist that already exists. So we do that. We insert. We had a successful insert. And if we do select all from artists, we see that Nizi Boskarizi's in there. But if we run this query that we did before, which is an inner join, we don't see him appearing in this artist table. And that's because an inner join is saying only show the data where we have a clear artist matching with a clear album. If instead we do a left join, he shows up. because we're saying show every artist, and then if you can, match them with an album. He has no albums released, so he's not being matched. He's still showing up, but they couldn't match him with the second table. But that's the difference between our inner join, so where we have the left table and the right table, we have a clear match on everything, and a left join, where we'll just include everything that comes from the left, and we'll only include the albums that match with a clear artist. An outer join, that means we'll include everything, even if there's a artist that doesn't have an album, he'll show up, and if there's an album that doesn't have an artist, they'll show up as well. Right outer join, this is an uncommon join because it has like duplicate functionality with left join. So if we have this right join where we're selecting from artists, we're right joining on albums, you can do the same thing with the left join, where this should be left, where you're choosing the album first, left joining it on the artist. So most people just don't end up using the right join, they just inverse, they change where they're selecting from and they change what they're joining with. You can flip both of those around and change from a left join to a right join pretty easily. A cross join's a also like super uncommon join. When you have a cross join, it'll return every artist from the left table matched with every album from the right table, whether or not that makes sense. So we'd have Kanye West matched with every album that was released by every artist, and then we'd have it's just all the combinations. So it's never used, but the note here is that if you do a filter on it, so if you did a cross join and then you say where artist ID equals albums ID, it's the same as an inner join. So you have every combination with every combination, and then you're filtering it down where you only have artist ID equals album ID. The same as the inner join. Therefore, you're not ever going to be using a cross join, but it's just in case you see it anywhere. The last two things we're going to look at are update and delete. So update and delete are much simpler queries than the select, but that doesn't mean they don't have a high level of importance. They're the most dangerous queries because they change or remove data. If you're doing update and delete queries without being really careful, you can do a lot of damage to the data that you have stored, and you don't want that happening. Especially, never use an update or delete query without a where clause. So why wouldn't you do an update and delete query without a where clause? So if I have yeah, exactly. If you're not specifying a where clause, your update's going to occur on everything. So for example, if we want to do an update, we can go like Nizi Boskarizi, his career is taking off, but his name's a little too wordy, so we want to shorten it down just to Boskarizi. So we can say update artists, and we can set the columns that we want to change. So we want to change his name, and our where is we're selecting just for the artist that we want. If I didn't include this line, then it's just going to set everyone's name to that, and that's why it's really dangerous to do either of these without a where clause. So if I save that, we run that query, we can see there was one update, and if we select everything, we see the new name, Boskarizi. Delete is similar. We can go, where's it? Oh, delete from, and then we specify a where. So, maybe Nima gives up the game, and we go delete from artists where ID equals So we save that. We run it. It says 1 delete, and we don't see his name in there anymore. So be careful when you're updating or deleting. There's also an argument for like, why would you even delete data? People say like, if you're putting useful data in your database, what's the point in deleting it? Some people, instead of deleting, they say create a new column in your tables called deleted at, and if the thing's not deleted, if it's data that you actually want to use, just leave it as null. And then if it's, you're wanting to remove it, you don't want it to show up in your queries, you don't want it to show up in listings in your web application, you can store a date in there. And then all queries you do, you just also add an additional where clause where you're saying where date is null. This way you can still filter out deleted results, but you can also, maintain that data in case later you want to use it for something, in case you make any mistakes. And storage is not expensive. So as we're deleting stuff, it's not a big toll on our database if we have old deleted things that we're using there. That's just an option. You don't need to use a deleted at column, but it's one thing to think about. Is this data that like I for sure never want to see again? Or maybe I'll like keep it as reference for the time being with a deleted at column. We'll look at this in the breakout a bit more. We talked about on delete cascade. But that's the time we have for now. I'll be around. Let me know if you have any questions. And I think also with SQL, it's really something that today you'll just be diving into writing queries. You'll get more comfortable with how to use it just through experience. It's kind of hard to just show a query once on here and for everyone to just understand exactly how to interact with it. I think the activities today will really give you a better grasp as you go through each of the steps and activities. So, cool. Thanks, guys.